Okay, I will speak about physics-informed neural networks for solving grayscale systems. This is a joint work with a model laboratory, mathematical modeling and data analysis laboratory that is in Naples at Federico II. And this is a work in collaboration with the guys and friends of our laboratory. Okay, about the talk, this is a brief overview. I want to introduce you some topics about scientific machine learning. After I will speak about physics-informed neural networks, some elements of learning theory of PINNs, and finally an application in engineer one about the grayscale system and some numerical experiment for 1D and 2D system. As just stated with Egidius, I am a mathematician, so the focus of this paper is about mathematics and also the application this kind of mathematics to an engineering problem. So about scientific machine learning, it is clear that now in the artificial intelligence world, where the very hot word at this time is IE or machine learning or deep learning, the data and the models are combined together in order to have a very good predictions. So the meaning of scientific machine learning is to incorporate physical law and domain knowledge inside the problem in order to have numerical methods that are much more efficient and accurate in the computation of a numerical solution. In scientific machine learning, our problems are typical differential problem, in which we have omega, that is a subset of RD, with the boundary, and F and G are data known on the domain omega and on the boundary. F is a generally nonlinear differential operator, and B is the boundary operator. For example, the boundary condition is Neumann or Robin and so on. Gamma is a parameter for the problems, and here zeta is the variable for space-time that indicate the related parameter to the physics. Now, on these settings, physics-informed neural networks are very interesting and novel paradigms for solving by using deep learning this kind of problems. In numerical analysis, classical approaches are based on Galerkin method, mesh-free methods, or so on. Now, physics-informed neural network is a very important alternative to classical numerical analysis to solve this kind of problem. And it is very interesting because it can help us to solve directly the problem or finding the solution or use physics-informed neural network to estimate parameters of a problem. So with PINNs, we can solve direct or inverse problem in scientific machine learning. So the basic idea underlying the physics-informed neural network are deep learning. What is a neuron? A neuron is a set on which we have a subset of RN inputs data, some weights, and a number that is named bias, some hyperparameters for the neuron, and two important functions. The first one is a parametric function that depends by weights, hyperparameters, and bias that is named the aggregation function, and the second one is the activation function. Now, what about the activation of a neuron? To activate a neuron, we have to apply a map for capital M to R, in which we have the composition of the two functions, the aggregation and the activation one, on the neuron eta for the parameters W, B, and theta. About this definition, we can connect some neurons each other in order to have a network. In this slide, I will present a very famous kind of network that is a feed-forward, fully connected neural network, on which each neuron is connected to another one. To have a response of a neuron to a level L, we have to apply the activation function, the composition capital F, to a linear combination of weights and biases applied to neuron. So this is a very, very basic introduction to neuron and neural networks. About this introduction, we can observe that physics-informed neural networks are a framework on which we can think that if we have a few data, our problem is described from the physics. So in this kind of small data regime, we can observe that non very few data, it means that everything is described by the physics of the problem. In the regime of big data, we have not so much information on physics, so everything is data-driven modeled. We can think to a physics-informed neural network as a kind of a combination of these two kind of regime on which we can integrate data with physical law in order to build up novel models that solve problem, take into account data and physics each other. In a practical point of view, we can observe that in a physics-informed neural network, the solution U of a differential problem is predicted by using a neural network that computes an approximation of U at theta zeta of the problem. So the physics-informed neural network is composed mainly of three parts. This is a pipeline in which we have a neural network for approximate the solution of the problem. And here we have some information about the physics of the problem, so the so-called physical law, and a learning process that is essentially the minimization of a cost function that is a so-called feedback mechanism that is help to this pipeline to compute an accurate solution of the problem. About the first part of the physics-informed neural network, or the neural network, we have a lot of family of neural network that is possible to implement in a PINN. The most famous one is the feed-forward neural network, but we can observe that there are a lot of papers that discuss the neural network part with other kind of architecture. For example, the convolutional neural network or Bayesian neural network. About the scientific machine learning problem, we have to observe that the topic of physics-informed neural network is quite it's quite young. In fact, in 2018, we have about 30 papers from the first one of RIC that discuss of this kind of topic. And here we have a sampled problem that is the Schrödinger equation. But the number of papers go exponentially. In 2021, we have 1,300 papers about PINNs. And here in this year, many very difficult mathematical problems are addressed with PINN. For example, nonlinear Navier-Stokes equations. In 2022, now at 6 months, this kind of growth is very exponential. So we have a lot of papers that discuss about PINN in scientific machine learning. Now, the learning process is generally driven by minimization of a dispersion function that is generally named the loss function that depends from the physics of the problem, the boundary condition, and from the data. By practical point of view, if you want to implement a framework that minimizes this kind of feedback mechanism, we have to consider some collocation points inside the domain on the boundary, and we have to discretize the loss function in such points. One of the most famous loss function is related to mean square error. So a way to model the learning process is to define a loss function, for example, for the physics of the problem by using directly the mean square error that is defined here. And in the same way, we can define the loss for the boundary condition from the data. The three main ingredients about the learning process are the differential equation, the boundary condition, and the data. Now, we want to focus our attention about some theoretical aspect of PINNs. In a classical numerical analysis framework, we want to compute an approximation of an exact solution of our problem by using a numerical method, for example, the Galerkin methods or finite difference methods or finite volumes and so on. The main theoretical issue is to have some theorem that tell us that the global error is equal to 0, or find a method that for a combination of parameter theta give us that this kind of error goes to 0. Now, in the PINN framework, the history is quite different because, first of all, it's not very clear what means the convergence in the PINN framework. Here we can try to formalize with our friend on Naples how mean the convergence in this kind of framework. Here we want that the neural network compute some predictors u at theta that can converge to u when n go to infinity. But in other words, the neural network is described by some hyperparameters. So if we consider the cardinality of this kind of parameters, we have a hypothesis class set that describe how the neural network approximates a function. So, for example, if this kind of cardinality go to infinity, the network is very expressive. So, in the sense that this kind of hypothesis class can approximate the function very well. For this kind of topic, we can refer, for example, that if we have one network with a network with one layer and the number of neurons that go to infinity, we have a so-called Shibenko theorem that guarantees us that the neural network can approximate as well as possible a continuum function. So the theory about convergence is very new and have to be formalized and to be addressed at this time. Go on this way, we can observe that in the learning theory, it is necessary to define the overall error inside the usage of PINN. The first error is called the risk. That is the risk of using the predictor u hat theta instead of the exact solution of the problem. And the discrete version of this continuum measure is at u theta, that is the empirical risk. Now, the main goal of an error analysis about this PINN is to find some theorem that give us suitable error estimate for R u at theta star, where R u at theta star is the last approximation computed by a trained PINN neural network. So this is the star stay for the end of the training process for the neural network, the last predictor. So by using this definition, we can observe that three main errors occurs when you use the PINN in this kind of framework. The first one is strictly related to some optimization task because we have minimized the loss function, and this kind of error is named optimization error. Now, after we have a kind of error that measure the quality of our prediction on unseen data, and this kind of error is named generalization error. And finally, the ability of a neural network to approximate the function U of our problem is generally named approximation error. A very, very new result on global error is due to Kutiniok in 2022 that give us a formalization of global error in terms of optimization error, generalization error, and approximation one. Another very interesting theorem is of Derrick and Mishra in 2021 of the ETH of Zurigo, that for a very, very specific neural network with two hidden layers and an activation function that is a hyperbolic tangent, it is possible to give a stability in subole space estimate that depends from collocation points and the dimension of the space. On this track, we can also mention two very interesting results of the Rick and Mishra in 2022 for the Navier-Stokes equation, on which we have a bound for that suffer of a course of dimensionality, in the sense that the bound depends from the number of collocation points and the dimensionality of the space. And for the Kolmogorov type PDA equation, for example, the Black-Scholes, the same authors give a result that is very interesting because not depend by dimension of the problem. So in this first part of my talk, I recall the main result by mathematical point of view about the theory of PINN. These results are very new and very few research groups in the world stay working on this topic. So I want to encourage you to address some theory and theoretical aspect about PINN, because this gives us the possibility to use this tool in a lot of problems or in a lot of scientific machine learning problems. Now, come back to our talk. The second part of the talk is devoted to Gray-Scott system of equation. The Gray-Scott system is a system in which we have two chemical reactions. We have a capital P and inner product that obey to this kind of chemical reaction. And we want to study the diffusion of the U and V obeying to this chemical reaction. The partial differential equation is described of two partial differential equation system on which you have two main parameters, capital F and K, that are the feed rate and kill rates, and tell us how U and V are distributed in this kind of reaction diffusion problem. The problem is known that to be difficult because it is highly unstable. Alan Turing discovered that only for few configuration, capital F and K, it is possible to observe the diffusive phenomena. So these phenomena are called Turing patterns. From this problem are known stability results for, and so for the Jacobian of U and V, it is possible to classify stable, unstable, and unstable configuration by studying eigenvalues of the Jacobian of the problem. This is very interesting because here we have a diagram with a bifurcation line, which we can observe that on this line bifurcation we have the pattern of the Turing patterns, so some configuration of stability of the problem. Inside of the domain, we have no pattern, and outside the domain, we have other kind of pattern. In this animation, it's quite clear that up to the animation, we can observe the formation of bifurcation line. Inside the bifurcation line, there is no pattern. Outside, in some zone, we can observe the Turing patterns. And in the button on this slide, we can observe the so-called mitosis reaction diffusion problem, that is a biological problem one, on which we can observe the reaction diffusion pattern and some specific pattern of Turing pattern for this kind of choice of capital F and K couples. Now, about us, we have implemented a new physics-informed neural network for the Gray-Scott systems. And here we can observe that in our network, we have the input, the collocation point, and some numerical data that are unsupervised, that are supervised data on the problem. Here we are the neural network that is a feed-forward neural network. Our output is about 2 neurons, one for U and another one for V. The feedback mechanism is computed by using automatic differentiation. And here we have information about boundary condition, the physics of the problem, and the data. More specifically, in our problem, for 1D Gray-Scott system, we have a loss function that depends only by the boundary condition and the physics of the problem. So here we have the boundary condition and here the physics of the problem. For the physics of the problem, the residual of physical or computing with function f1 and f2 respectively, as reported in the slide. So this is the core of our loss function. And we carried out two kinds of a numerical experiment. The first one is about an exact solution. In a specific case, we can know the exact solution of the Gray-Scott system for 1D problem. And the second one is a comparison with the Galerkin methods. Our accuracy metrics are about root square mean square error. And the computational cost is quite high because we have 5,000 epochs for the convergence and 1,000 epochs for the patients. And thanks to the laboratory model, we have the hardware on which we can run our problem. And the hardware is a NVIDIA 3080 GPU on which we can run the model. Now, by a practical point of view, in this kind of configuration for F and K and a selection of a variable for changing variable inside the system, it is possible to find the two exact solutions for our problem. In this picture, we can observe that the predicted values of the PINN, that are continuous line, are very well predicted with respect to the analytical solution of the problem. And this is confirmed by root square mean error as reported here in the slide. About the Galerkin method, we have some initial condition, boundary condition for which it is not known the solution. So we compute the solution of 1D Gray-Scott system by using Galerkin methods. Our architecture here is of 4 hidden layers and 20 neurons. We use the hyperbolic tangent as activation function, the Adam optimizer, and for this configuration, we have some comparison with the Galerkin methods for several points. So here there is some comparison with the same number of points. And the table 2 is much more interesting because we fix to 15,000 points for Galerkin methods, a super solution of the problem, and we compare the PINN with the full solution by selecting respectively 24 and 600 points. Here we can observe a sort of convergence to the Galerkin method's computed solution. Here there is much more less informative pictures in which we can observe the wave, the behaviors of the PINN computed and the Galerkin 1 solution, and it's quite the same as confirmed by the tables. Much more difficult is for us the 2D Gray-Scott system, because in 2D Gray-Scott system we have to predict a 2D pattern configuration, and for this kind of problem we have to introduce a loss related to the data. The main idea is to compute some slice of the solution by using Galerkin methods and use this kind of data as a supervised one for the PINN to try to predict the reaction diffusion problem for a long time. This is our configuration about space-time domain and initial condition, some periodic boundary condition, and this is the idea. For some fixed points, we select a slice of solution and try to simulate for overall time the reaction diffusion problem by using the PINN, but the data are imposed at some time inside the PINN in order to have the solution of problem. Here there are some configuration. For example, if you use a capital F as this value or that one, we can observe some slice of the diffusion pattern. For T750, we have this kind of pattern, and to T equal to 4070, 50, we have this pattern. This is a classical flower pattern. Here there is the mitosis as just viewed in the video, and for selecting capital F and K as T2 value, we can observe this kind of pattern. And for soliton, we have the same one with several configuration. And finally, for zebrafish pattern, we have this kind of pattern when F and K are selected as these two kind of number. I want to highlight and focus your attention that predict a solution for a 2D problem is very difficult, and it is a limitation on PINN for which if the time go up, the PINN compute a very inaccurate solution of a problem. So for our for correct this kind of lack in the PINN methodology, we use a supervised strategy, imposing some slice at each time as data in order to compute this pattern that is quite accurate. Here there is a table that reports errors about flower mitosis in soliton, zebrafish, but the trick was to supervise the problem. Now, finally, I want to conclude you with a very few sentences, because physics-informed neural network are very interesting new methodology in scientific machine learning, and help numerical analysis and engineer to solve a problem directly by training a neural network. For many scientists, this kind of approaches based on neural network are generally viewed as a magic black box and is not so solid as a finite difference method or Galerkin 1 in numerical analysis. This is not true now. A few years ago, many mathematicians say that this kind of methodology are not so formal or rigorously explainable. Now, thanks to some results that are very recent, as I have just showed you in the previous slide, it is possible to have stability and convergence theorem about PINN. And this tell us that this kind of methodology can help us to efficiently and accurately solve problems by improving numerical method and more in general scientific computing approaches. About research direction, with the modal group, we have published a survey on that is now on archive, and we have improved this paper by following suggestion of a reviewer. So in the next month, we hope that our paper will be published in a final form. And another aim is to use a physics-informed neural network to solve a 3D grayscale system that is much more complicated. That is one. Here there is a very little brief bibliography on this topic. And finally, I want to thank LiveDat for a gentle invitation, and also my colleague and friend of Naples to support me on this talk. Thank you.